So this is just a tiny bit of review. You guys didn't seem to do much better than my night class did on the last lecture. I just don't understand the difficulty of 1 minus x, but hopefully today we can work through that. So, K sub C in this case, these are in moles per liter, molar, all right? In this case, look at that, it says equilibrium, 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 equilibrium. That is the equilibrium concentration, okay, with the coefficients being the exponents. When you've got the equilibrium values, if I give you all 4 equilibrium values, you can give me what K sub C is equal to. Okay? I can ask that question. However, if I say that you start with this, okay, and that's like the sandwich analogy, okay? You start with 26 pieces of bread and 3 tomatoes and 6 heads of lettuce. You know, how much of this stuff can you make? Okay. This is going to tell you basically which way the reaction is going. Initial concentrations go into this. Q sub C, initial, 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 initial. And this just tells you which way the reaction is going to go and helps you determine whether something's going to be 1 minus x or 1 plus x or 1 minus 2x or 1 plus 2x, that type of thing. So that's what Q sub C does. So this is how it works. If the Q sub C is smaller than the K sub C, the reaction goes that way. If they're equal, equilibrium, no change. And if the QC is bigger, then it goes from products to reactants. Okay? So it goes this direction, no direction, or back to here. Okay? So if K sub C is bigger, it's got to move back this way in order to get lower. That's it. Okay? So once again, we briefly touched on this the other day. Homogeneous. Jeez, I would have taken. Said homo. Okay, never mind. Had nothing to do with the word. Okay, homogeneous. Okay, means the same phase. There are 3 phases: solid, liquid, gas. Okay. This is the same phase. Homogeneous is when we're doing gases. We can have liquids, all right? So, in this case, we've done this before. Here's the way the reaction is written. Okay, the reaction here is N2O4 breaks down and forms this, all right? So, if we look at the K sub C, even though this is a gas, you can have molar. All right, and the way they've got it written here, this is molar, okay? So you've got the coefficient there is a 2, and therefore you go products over reactants. So here's the products here. So you're going to go NO2 squared over the concentration of N2O4. That's how you write it up. And I can either give you the equilibrium concentrations, I can give you the equilibrium concentrations of okay, now here's a question. K sub C is equal to 3. And the equilibrium concentration of NO2 is 6. What is the equilibrium concentration of N2O4? What'd you get? 12. That's the answer. Okay? How did we get that? Well, I think I said this was 3, thank you. This was 6. Okay, so 3 and 6, I don't know what this is. So I got to solve for it, right? So I put this over here, pull this down here, and I end up with 6 squared is 36, divided by 3 is 12. Okay? That's how you do it. So that's a very simple little question. They get tougher after this, but basically you cannot forget that coefficient. Okay, now, if instead you're given pressure, and not moles per liter, but pressure, then it's this. K sub P is equal to, and this is the same thing. That 2 there is the square. Okay, so it's the pressure of the NO2. Okay, that whole thing, it just says that the pressure of the NO2 squared divided by the pressure of the N2O4. Okay? So, what is K sub P if the pressure of N2O4 is 400 torr and the pressure of N2O is 400 torr? What is K sub P? Nope. What's the answer? 400. Right? If this is 400 squared and this is 400, that's why you don't need units. Just 400 divided by, or 400 squared divided by 400 is 400. So K sub P would equal 400. Do not forget the coefficients, folks. Okay, in most cases, K sub C is not equal to K sub P. So, delta N, here's the equation. You must know this equation. Absolutely memorize. K sub P is equal to K sub C. RT, and this whole thing is to the delta N. Delta N, you calculate by the number of moles on the product side minus the number of moles on the reactant side. Okay? So if you look at this equation up here, what is delta N? 1. 2, take away 1 is 1. Okay? Moles of gaseous product on this side minus the moles of gaseous product or reactant on that side. 2, take away 1 is 1. So what if, folks, if I say that K sub C is 1? For this equation, what is K sub P? What is, I want a number, not a philosophy here, okay? What is K sub P if K sub C is equal to 1 for this reaction up here, where this is a 1? You got it? What's the answer? Oh, you need temperature. Thank you. 300. What is it? Units. For what? Oh, 300 K. And don't forget, folks, we've got pressure. This is, we have an R that is in atmospheres, right? That's the one you want. So it's just going to be 0.08205 times this to the first power. Okay? So what is K sub P if this, what did I say this was 1? What is it? 24? Who got 24? Okay. So this, folks, is posted. It is straightforward, and as long as you understand and have memorized this equation, and you can plug these things in. So don't come to the final and not having practiced this. Okay? You need to practice this a lot. Okay, question. And you can't answer it. He was in last night's lecture. So it says K sub C is not equal to K sub P. Okay? In certain cases it is, though. How can K sub P equal K sub C here? If delta N is equal to 0. Because if something is to the 0 power, this whole thing becomes 1. That is a wonderful multiple choice question. Okay? Under what situation is K sub P equal to K sub C? When, you know, when you have the same number of moles of gas on either side, when you have the same number of molecules, you know, whatever. I'll come up with some way to write it. You see, if that's a 0 right there, folks, this whole thing becomes a 1. A little bit of trivia. Okay, do this. The equilibrium concentration for the reaction between carbon monoxide and molecular chlorine to form COCl2 at 74 degrees C are, and these are molar concentrations. I'm not used to working in molar concentrations for gases, but here we are. Molar concentration of CO, 0.012 moles, Cl2, 0.054 moles, and CoCl2 is equal to 0.14. Calculate the equilibrium concentration, the constants, the equilibrium constants K sub C and K sub P. So let's first do K sub C. K sub C.
I got 216 and this is 220. So
Okay.
I guess.
Okay, who's got a K sub C? Raise a hand. What'd you get? 21.6. No. You're off by a factor of 10. What's that? About 220 atmospheres, or per atmosphere, I think is what it is. Okay, now, who's got K sub P? So K sub P, you got to take that K sub C and put it into that K sub P is equal to K sub C times RT delta N. Who's got an answer for that one? What'd you get? 7.5, 7.6, something like that. Okay, let me, I think I'll show you how it's done here. Okay. So maybe you just, young lady here, maybe just poked in the wrong number on your calculator. Like a 0.54 instead of a 0.054. So that's about 220. And then yes? Moles per liter. No, this is molar. That's the definition. The definition is that when you use, it's either in pressure or it's in moles per liter. Yeah. Mole fraction is when we're making changes to freezing points and boiling points and that type of thing. Okay. Any questions on this? Straightforward, plug and chug. Okay. Absolutely have to remember how to do that. And folks, it's critical that you know how to do your delta N. Okay? If you get your delta N wrong, you get everything right. You get your delta N wrong, numbers wrong, you can't get more than half the points. Okay, I want everybody to look at me for just a second. So, on the final, I don't want anybody to ask me any questions after this. The final, folks, is 2 hours long. Your exams have been a little over an hour. So each exam has been about 20 questions. So in theory, the final will be 40 questions. Right? Twice as long. But it won't really be 40 questions because what I plan on doing is instead of having several 4-point questions, I'm going to have more of the 8 and 10-point questions. And there'll be some 4-point questions for Chapter 10, okay? But it's going to take a long time to grade this thing. And so one way to speed up that process is to have questions that are a little bit more extensive. So just be aware, the final will probably, it'll maybe be 40 points of multiple choice instead of 20. I don't know. and then the rest will be free response. The last question will be the same. The last question will be the same. We have to get it all right. About 50 points will be chapter 10. 50 points is just this stuff. And then the rest will be review. If you can do the exams really, really well that we've had so far, and go through the lecture, I mean, I'm only so creative. I can come up with variations on a theme, but there's only so much I can do. Hess's law is Hess's law. And so a lot of the problems will be similar, not the same numbers, but the same type of things, okay? So please, no more questions about the exam. It's 200 points. You get 160 on it. You get an automatic A in the class. I'm hoping that the average is around 110, something like that. Okay, that's sort of at the average that we've been. So, yes?
For that problem, can you explain why it's 220
Okay, so I should have gotten rid of that. So usually when we're talking, I mean, we have this implicit rule, okay? I should have just had 220, okay? You will not get it off if you don't have, if I say what is K sub C, and if you just said 220, you get 100% on the exam, okay? Once again, it's nice to keep track of the units, all right? But you do not have to, okay? I just like units because they tell me what to multiply by what and what to divide by what. All right, so there will be a problem like this on the exam. Do this one. At equilibrium, the equilibrium constant, K sub P, for the reaction 2NO2 goes to 2NO plus O2 is 158 at 1,000 degrees K. What is the equilibrium pressure of O2 if the pressure of NO2 is equal to 0.4 atmospheres and the pressure of PNO is equal to 0.27 atmospheres? Now, folks, before you start, look at how big that that equilibrium constant is. 158. Okay, 158. What does that tell you? That tells you it's almost completely over there, right? If you have a K of 1, it's sort of, the concentrations are somewhat equal. If it's 0.00001, it's all on this side, almost all reactants. In this case, 158 is pretty darn big. So I'm just telling you that whatever's on that right side is going to be, there's going to be more stuff left over on the right side than there is on the left side. Yes? What's that? Q sub C? If you want to do Q sub, yeah. Q works that way, yes. It'll tell you which way things are going initially. Okay, but this says, see, what is the equilibrium pressure of this if the pressure of this is this and this is this, okay? So, you set it up like this. K sub P is equal to the pressure squared of NO, right there, times, there's a coefficient of 2 there and 1 there, so this is the pressure of NO times the pressure of O2 over, once again there's a coefficient there of 2, the pressure squared of NO2. And we already know what that is, right? So we're given this, 158. You plug those numbers in here, you got 158 times that pressure right there, times this pressure right there, each squared, so you come up with a value of the pressure for oxygen is 347. So folks, this would be a, I don't know, 4 to 6 point question on the exam. Any questions on this? So just sit for a second and listen to this. I haven't done a lot of theory in this class, but this is the Gibbs free energy, and this is the progress of reaction. What I mean by progress of reaction is that if I have a, 2 beakers and I'm pouring them into some reaction vessel, that is the beginning right there. And the progress of the reaction is sort of how the whole thing of, in this case, right here is pure reactants, which means I haven't really poured it together, and this is if I had pure products. Okay, so if I have pure products, is at the absolute end of the reaction. Pure reactants is at the beginning of the reaction. So if you look at this, look what happens to G. Delta G, is it changing? What is delta G doing here? Getting bigger or smaller? Smaller. So delta G is negative here. All along here it's negative. Spontaneous, 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 spontaneous. Equilibrium right there. Okay? So from here on, it's not spontaneous, okay? But if, for some reason, I dump in some of the pure product, guess what? It's spontaneous going this direction, okay? So this is the minimum right there, all right? If you're coming this way, the delta G is negative. If you're coming this way, well, not this way, like this, it's negative, okay? So, on the next slide, this will illustrate what K looks like, okay? So, if we have pure stuff here, pure reactants, pure products, pure reactants, pure products, if you have a big K means it favors the products. Look at this. Look at how the reaction, right here, the equilibrium is right here. See where that minimum is right there? Right there. It's almost all pure products. Okay? So this would be the free energy diagram in terms of the reaction progress of something that has a very big K. This one, look at this. You don't get out of starting blocks on this one. You start, you add it together, and it reaches equilibrium quickly, and it's very happy being just almost all reactants. So this has a K that is much smaller than 1. If it were right here, okay, right here in the middle or right here in the middle, then K would be 1. Okay, so I just want you to have a feel for how this works, okay? I could have a figure on the exam that would say, so you're at such and such a point, is this spontaneous or not? This is a cartoon of what that looks like, okay? This, if we're saying that blue are reactants and the gold is the product, if you look at this first one, you'd have to say, K is not very big. Is there very much product in this top one? No. K is equal to, 0.1 or 0.01 or something like that. Where you then have it where it looks like it's about equal, okay, you got a K of 1. And then when you've got one where it's mostly products, then you've got a big K. Okay, so this is the kind of conceptual thing I would expect you to be able to understand and identify on an exam. And once again, if Q is smaller than K, you need to go to your right to reach sort of this equilibrium. And if it's bigger than K, you come back to your left. So, up until now we've talked about homogeneous stuff. Now we're going to talk about heterogeneous stuff. So here we have calcium carbonate in this little vessel. Here we have a little bit of it. I'm assuming that from this picture that the calcium carbonate is, well, I'm not really sure what it is, but whether that's the red color, let's say it's this red rusty looking stuff. And over here we have a certain amount of it, and there's a lot more green in this, which is the calcium oxide. And look at the pressure. How many CO2 molecules? This is the reaction right here. How many CO2 molecules do you see above the solid here? 6. So now we add a bunch more of something. Okay, I don't know whether we've added calcium carbonate, or I guess that's what we've done. We've added more calcium carbonate, or we have less of this. Okay, so we've changed significantly the amount of this and this. How many molecules of CO2? 6. So the solids and the liquids, folks, they don't affect this. Okay? It's only the gas that we worry about. And last night, I don't know, I had a hard time explaining to the class how this works. But let me try with if this were just water. Okay? And let's say it's room temperature, 20 degrees. The vapor pressure of water at 20 degrees is about 20 torr. Okay, 20 torr. If I heat it up to 100, what is the vapor pressure? If I heat this water up to 100 degrees C, what is the vapor pressure? 1 atmosphere, right? 1 atmosphere, the boiling point. But at room temperature, it's about 20. So so right now I've had this top on long enough that I have reached equilibrium. I have 20 torr of water vapor in this headspace. Okay? But if it were filled up to here, instead of down to here, I would still have 20 torr of water vapor up here. Doesn't matter how much water I've got. As long as I've got even 1 drop, I have the vapor pressure of water up here is 20. Okay? And what we're looking at, folks, with these kinetics kinds of experiments is what is the pressure. Okay? And in this case, the pressure of the water in here would be 20 torr. And so this is exactly what is happening here. Okay? By adding a bigger pile of stuff here, it doesn't affect this. So when we do these types of equilibrium problems, you only worry about things that are in the gas phase. Okay? So look at that. K sub P is equal to the products over the reactants. This doesn't count. That's a 1. Okay, you give these guys a 1. The solids get a 1. So basically you've got the pressure of CO2 times 1 for that over this, which is 1. So basically your K sub P is equal to the pressure of CO2. So in a system like this, it's very quick. You look at it, you say, oh, the only thing I'm worried about here is the CO2. So in a heterogeneous situation, the solvent, the liquid, and the solid don't enter into equilibrium. Let me see. Let's, okay, well. So once again, this is sort of the same thing. Solid, solid, gas. Okay, so K sub C here would equal the molar concentration of CO2, and the K sub P would equal the pressure of CO2. So they are different. Okay, why? What is delta N? What's delta N up here? 1 take away 0. So it's 1. So it's got to be different. K sub P has to be different from this unless there had been a gas on this side. If there had been a gas on this side, it would have been 1 minus 1 would be 0. And then K sub P would equal K sub C. So here's just a couple cartoons that show, so what is it saying here? For the reaction, this is iodine solid going to iodine gas. What happens to the vapor color intensity? And that's sort of the color, not quite, but of iodine gas, I2. When you add it, see this little pile of iodine here? They say, what if you add more? What happens? So what's going to happen is the color going to get deeper purple. So it kind of looks about like that. Is it going to increase, stay the same, or decrease? It's going to stay the same, because it doesn't matter how much you pile down here, the amount up here, the pressure, not the number of molecules, because obviously if I filled it to right up to here with this stuff, the number of molecules in here would change, but not the pressure. Okay? Independent of the solid, stays the same. How about this one? What if we put a little heat to this thing? What happens to a solid when you heat it up? Or a liquid when you heat it up? The vapor pressure increases. Okay? Take water and heat it up. What happens to the vapor pressure? Boom. Okay? So you do this, you can actually force something into the gas phase. And so this is it. So look, here is the solid gas line right here. All right? And as we increase temperature, what's happening here? Boom. So the answer is that it's going to increase. All right. Do this. So it says, consider the following equilibrium at 295 K. NH4HS solid is in equilibrium with NH3 gas plus H2S gas. The partial pressure of each gas is 0.265 atmospheres. Calculate the K sub P and K sub C for the reaction. So folks, if you're asked this, you have to know that these are the equilibrium partial pressures. Who's got an answer? What do you get?
Oh, I just got 0.265.
0.265 for KP. How many people made that mistake? This is a solid, folks. Oh, gosh. It's a solid. Don't you think I was going to do that? I just gave you 3 things that are solids, and I said you got to make sure you don't mistake this. And then what do? Half the class, just like last night, ends up not seeing that S, okay? You've got to look at the phases, folks. Heterogeneous chemistry, remember? So this is K sub P. What's K sub C? How many got a delta N of 2 instead of 1? How many got 1? Okay, so you subtracted off the solid, which you shouldn't do. This is just gases. Moles of gases. This has 1 mole, 1 mole. That's 2. N is 2. Take away 0 is 2. So that number goes as a 2 right there. Now, people last night were a little confused as to this rearrangement. You shouldn't be confused. Okay, it's quite simple. So we had a K sub P, right? You have calculated K sub P was equal to that. So if K sub P is equal to this, you put that right there. And if you want, You can solve this many different ways. I would probably just say 0.07 is equal to K sub C, and then this is all RT to the 2. Okay? And I would just multiply RT, get a value, and square it. Okay, so I would end up with a number right here. I'd have a Kp is equal to K sub C times some number, and then I would just divide this number by that number. But this is a way to rearrange it. However you want to solve the problem is fine, as long as you solve it correctly. Yes?
Where'd you get negative delta N?
Oh, okay, that's the, okay, because look, I've switched this. So once again, folks, K sub P is equal to K sub C RT delta N. Okay? But if I'm going to pull this right here to this side, it's the reciprocal. So instead of a, RT squared, it's RT to the minus 2. Folks, this is very simple math that you need to be very comfortable with, okay? Now, you don't have to solve it that way. As I said, I wouldn't have done that. I'd have just said, look, I came up with this number. I put that right there. I multiply RT. I get 16. I don't care. And then I'd be 16 squared is some number, about 200. And then I would just divide this by 200, and I'd come up with that number. So don't feel you got to do it this way. This is just a little mathematical manipulation. Questions? Okay. Maybe it gets more complicated right now. So, look at this. We've got two things going on. We have A plus B goes to C plus D. Okay, we're going to call that reaction 1. So that is going to be K sub C of reaction 1. Then we got another one. C plus D goes to E plus F. We're going to call that K sub C of reaction 2. Okay, so to start off with, what is K sub C of reaction 1? Write it down. What is K sub C of reaction 1? It's right there. And then what is K sub C of reaction 2? If you multiply these together, what do you get? You get K sub 1C times this, okay, or this times this. And look at the CD on top and the CD on the bottom. They just cancel out. Remember Hess's law? Same thing. So if you've got a situation where it's a two-part reaction, the K is equal to the K sub C's of each of those things times each other. Okay? So K sub C1 times K sub C2 is equal to the big K sub C. And C and D don't even show up in the equation here, okay? K sub C is equal to EF AB. Do this again in a little bit. Any questions on this? If a reaction can be expressed as the sum of two or more reactions, the equilibrium constant for the overall reaction is given by the product of the equilibrium constants of the individual reactions. So K sub C1 times K sub C2 is equal to the big K. Okay, so I'm going to give you this, N2O4 in equilibrium with 2NO2, both in the gas phase, folks. K is equal to that. Now, Here I'm saying N2O4 is going to 2NO2. Okay? And here is the K. What if instead I wrote it like this? What if I wrote it instead 2NO2? So I'm going this direction instead of this direction. What is the K? It's the reciprocal. So if this is 4.6 times 10 to the minus 3, then the K for this reaction is the reciprocal of that, 1 over that. Which makes sense. If we think of that reaction diagram, okay, if you've got a big K, then that means things are way on this side, okay? If I then say, okay, here's where I start, they don't go back this way. They still hang out over here. So it's reciprocal, okay? So just 1 over the K. So if I give you something, folks, where I say, here is K for this reaction. K for N2O4 goes to this, is that. And then I ask you, you need an equation where it's actually the opposite, it's this one. Then I'm not going to tell you what the K is. You're just going to know that it's a reciprocal. Okay? When the equation for the reversible reaction is written in the opposite direction, the equilibrium constant becomes a reciprocal of the original equilibrium constant. Okay, so this is just 5 little rules, okay, that will help you. Okay, you're not going to have to recite these, but that the concentrations of reacting species in the condensed phase are expressed in molar. Condensed phase means not gas. In the gas phase, the concentration should be molar or pressure. Okay, we've done ones that we had CO2 that was the molar concentration, and then we did CO2 that had the gaseous pressure. The concentration of pure solids, pure liquids, and solvents do not appear in the equilibrium constant expression. No matter how much solid you've got, there's giving no pressure, no extra pressure. The equilibrium constant is dimensionless quantity. In quoting a value for the equilibrium constant, you must specify the balanced equation and the temperature. Temperature is important, right? Temperature is not important if I'm asking for a K sub P and I give you some concentrations. But if you end up calculating K sub P and then I say, what is K sub C? That equation is K sub P is equal to K sub C, parentheses RT delta N. You need to have the temperature. And I forgot to give that to you earlier. Because the temperature makes a huge difference. If a reaction can be expressed as a sum of 2 or more reactions, the equilibrium constant for the overall reaction is given by the product of the equilibrium constants of the individual. That means you multiply them together. Okay. A little bit of I've alluded to this, but haven't actually done one. I said that at equilibrium, you have stuff going in both directions. They just cancel each other out. So what we have here is this. You're gonna have kinetics next quarter, a chapter of kinetics. And kinetics is where you say, okay, the concentration of A times the concentration of 2B here times the K. That's a small K. And that K is the rate constant. That's how fast things actually go. This actually tells you something about how fast a reaction will occur. The K equilibrium doesn't. K equilibrium just says how far it will go. It says nothing about how fast. So K sub F is the forward reaction. So it's going to be Kf times this, the concentration is what goes this direction, and coming back is AB squared, AB2 times the K reverse. Okay, so it's how fast it goes this way and this way. At equilibrium, they're at equilibrium. They equal each other, or the opposite each other. So the rate forward, once again, same thing, squared up there. So it's going to be K sub F times the concentration of A times the concentration of B squared. That's the rate forward. What do you think the rate reverse is going to be? Okay, K reverse times the concentration of that. So the equilibrium, once again, they're equal to each other. And we can say the same thing here. K sub F is equal to this. This is the products, is equal to this is the reactant side, this is the product side, that this whole thing is equal to each other. Okay? So K forward, K reverse is equal to K sub C. And that, once again, is AB, the products, over the reactants. Just a different way of looking at it, okay? The main point, though, is that K sub C, this is just another way to derive this, the K sub C is equal to the concentration of the products over the reactants, with the exponents considered. I'll review, okay? That the equilibrium is a delicate balance. Chemical equilibrium can be homogeneous or heterogeneous. This is the generic way of doing things, right? This is the generic way. Little a, big A, little b, big B goes to little c, big C, plus little d, big D, all right? D being the actual concentrations or the pressures, and these are the coefficients, okay? So, K sub C is equal to this. These are in concentrations. This is at equilibrium. These are the equilibrium concentrations or pressures for these guys, okay? So this is the pressure of compound C to the C power, compound D to the D power, and so on. And K sub P is equal to then K sub C RT delta. And it's not equal to this unless that's a 0. Study this. This is the same thing that we did earlier, okay, where you have this equation, A plus B goes to C plus D, C plus D, and this is just a little bit more of a derivation of that, okay, but once again, multiply them together. Okay, let's do this. Carbonic acid ionizes in water in 2 steps. H2CO3 in equilibrium with H plus and HCO3 minus, and that KC1 is equal to 4.3 times 10 to the minus 7 molar. The M's are red, it's just housekeeping. You don't have to put that down if you don't want to. Second reaction, HCO3 minus in equilibrium with H plus CO3 2 minus, has a K sub C of 5.6 times 10 to the minus 11. What is the equilibrium constant for the full reaction? Okay. So, the full reaction is right here. That's what I want to know. Okay. So what is the equilibrium constant for that? Okay. Well, look at Hess's law. Use Hess's law. Look up here and say, okay, on my left I need 1 H2CO3. The way this is written, how many H2CO3s are there on the left-hand side above us? 1. We're happy, okay? We got one right there, we got one right there. So now on this other side, we need some hydrogens. How many hydrogens do you see up there? 2? Perfect. How many CO3s? 1? Perfect. What are we left over? This guy, and they're on the opposite side. So they cancel, okay? So these actually, you just multiply together, you add them this way, you are going to multiply these two together to come up with the case of, what is the answer? Yes?
2.4 times 10 to the minus 17.
So she's got 2.4 times 10 to the minus what? 17. Perfect. So does this smell of Hess's law, folks? Yes, it does. It does. Okay, so don't be surprised if that doesn't show up pretty soon. But that's exactly right. The K sub C is equal to this. These were not pressures. These are in concentrations, okay? Uh-oh. Dr. Hess returns. So, you know the equilibrium constants for the following reactions. Sulfur plus oxygen gas goes to SO2 gas. That equilibrium constant is 10 to the 52. Sulfur plus 3 oxygens goes to 2 SO3 gases, and that equilibrium is 10 to the plus 29, 129. What is the equilibrium constant for this? Now, folks, I want everybody to just look at me for a second. Okay? I got some good and some bad news for you. most of you do not have a calculator that can handle a number as big as that. Try right now on your calculator to enter 10 to the 129. What's it say? Overload. Or something. What'd you say? Low? Check your battery. So you can't do it. Okay, that's a huge number. Okay? That's several moles. Okay? You can't do it. Okay? So you're going to have to come up with a different plan, and I'll tell you in a minute. Okay? So, folks, look at these. You got this. We just went over how you multiply stuff. Not sure why that got shifted over like that. But I want to know what this is. And you're all smart. Every one of you is smart. So you can figure out how to get around this overflow or overload problem. Hess's law. Is that a big enough hint? I'll give you a minute or two. So without cheating, who's got an answer? So how do we approach this? Okay, I'll give you a minute. Anybody up here with an answer? What do you get? Okay. Yes?
2 times 10 to the 77.
He's got 2 times 10 to the 77. Wrong. But good try. I think it's wrong. Yes? 10 to the 25? Ooh. Who's got 10 to the 25? That's correct. Now, here's what you got to do. Those equations, the first one that I gave you, was on the wrong side. Look at this. Okay? What do we need on the left side? We need 2 SO2s. Do we have 2 SO2s up there? We have 1, but what side's it on? The wrong side. So that means this whole thing needs to be multiplied by something or switched around, right? Remember when we did delta H's? When you did a delta H, you brought this to this side and all, and you changed the sign for the delta H. The delta H had been 100 kilojoules, and you flipped it, it's now minus 100 kilojoules. Okay, well, remember earlier, about 4 slides ago, I showed what happens when you have to move it from one side to the other. You take the reciprocal. So I can change this, I can flip this to this side, these to this side, multiply that whole thing by 2, and then I take that and I take it to the reciprocal of it. But you don't multiply by 2, you multiply times itself. Okay? So this number then becomes, look at that, 10 to the minus 52 squared, which is 10 to the minus 104. Very small number. Can you do that on your calculator? Do it. I'm just curious. Okay, so you can go small, you can't go big. Okay, so what we have now is we have, look at what we've got up here. We've moved this around. We've got a 2s here and a 2s there, so we get rid of that. We got an oxygen, 2 oxygen on this side, 1 on here. Leaves us 1 here. So we have exactly what we need. Okay, you multiply them together. So you got 110 to the 129 here, and then you've got this times this squared, and you end up with 10 to the 25 per mole. Don't worry about the per mole. Yes?
So like in Hess's law, you multiply by the coefficient. Here you like.
No, Hess's law, you don't multiply the coefficient.
Okay.
You flip it.
Okay. So in this, like for the reactions, you raise it to that.
For the K.
For the K.
Yes, for the K, you take it to, if you need 2 of them, the 2 goes there. If you needed 4 of these, then it would be 10 to the minus 52 to the 4th power. Because it's like you got 2 of them, okay? You got, originally you had 10 to the minus 52 times 10 to the minus 52. Do we know how to do this? Raise your hand if you want me to do something. Okay, I'm going to assume you know how to do it. Now, these numbers were ridiculously large or small, and your calculators probably can't go past about 10 to the 100. So in this case, folks, you just have to do good old-fashioned math. Okay? Forget it being 10 to the 29 or 129. Just say, okay, I got 129, and I'm going to subtract 104 from it. You get a 25. Okay? And that's what that is right there. Okay, let's do this. At 1400 K, K sub C is equal to 4.7 for the reaction. And we're going to omit all that M stuff. H2O gas plus CH4 gas, equilibrium with CO gas and 3H2 gas. Which direction will the reaction proceed in a mixture containing 0.035 molar water, 0.05 molar methane, 0.15 molar CO, and 0.2 molar H2? So folks, if you're given this, and the question is which way is it going to proceed, this is just a Q question, okay? This is a Q, okay? Because you're given this. You're given K sub C. So all I'm asking you is Q bigger than K sub C or smaller? And which way is it going? This would be like a 4-point question. Yes? Oh.
How can you multiply if it's not the same units? Because this is n to the negative 1, and do we assume this is n?
You don't have to worry about the units.
Oh, so you just multiply. Okay.
Mm-hmm. How many got a Q of about 0.7? What does that mean? Is it going left? Oh, it's going this direction or this direction? To your right or left? That way. Because look at how big the K is. 4 something, right? 4.7. So we got a long way to go to get there. So things are going to go further this direction. So that's how Q helps us, okay? Q tells us whether you're adding something or subtracting something. Okay, should I move on? All right, now this one, last night's class had a real problem with. I don't understand why, but maybe my lectures fall apart at the end, I don't know. Or they were getting tired. This is an isomerization. Okay, look at this. Same configuration here, except this X is in the down position instead of in the down position is instead of this like right angle position. Okay, so it'd be sort of like if I took this bottle here and all I did was say, you got this bottle, and I take the top and I do that. Pretty clever. I can do it again if you want. Okay. That's an isomerization, okay? It's not something plus something goes to something else. It's this thing changing, okay? It's like if I had a hat on, I took the hat off. Put the hat on, hat off, okay? So that's what's happening here. So isomerization equilibrium constant for the following reaction, K sub C is equal to 9, okay? Calculate the equilibrium concentrations for the case when you start only with A. Okay, you have none of this, you start only with this, only this, and you start with 1/100 of a molar. So 0.01 molar. So you start only with A, you've got a K sub C of 9. Okay? Do it. So you start only with A, and when you're done, you're going to have some A and some B.
Is this just like last times with the subtracting?
Good job. So a little hint, folks. A little hint is that you started with this. For every one of these that you lose, you make a B. So if I want the equilibrium concentration, yes? 0.009, he says, for A. So what he's saying is that you start with 0.01 and you end up with 0.009. 0.009. For which one? For A. Let's see. Look, we got a K sub C of this. What does that tell us, folks? He meant B. Okay. So I thought. Okay, so what does that big K sub C tell us? Which way does the equilibrium lie? More on this side or that side? This side. The product side. Okay? So what do you make? So for every one of these you lose, you make one of these. Okay? So at equilibrium, if K were, let me give you an easier one. If K were 1, K sub C was 1, what is the concentration of B? So if the concentration, if the K is 1, folks, what does that mean in terms of the concentrations of the two? They have to equal each other, right? So how do I make this be half as big as it used to be? So this, folks, is going to go to 0.05, 0.005, and this is going to be 0.005. That over that gives me 1. Okay, so once again, for every one of these you lose, you gain one of these. So this is the 1 minus x thing, and this guy's right. Okay? Look at what happens. So you start initially, you have none of this, and all of this and none of this. So the change, you're losing. For every minus x here, you gain an x here. It's the same thing, it's just morphing. So everyone you lose on this side goes to this side. So whatever this is in minus is going to be a plus x over there. So the equilibrium is just going to be 0.01 minus x. And what is this going to be? Right. Okay. So you know what your K is, right? Look at that. K sub C was equal to 9. So concentration of B is x. Concentration of A, we said, is this. You solve for x. And you get that x is equal to, as this guy said, 0.009. Okay? That's almost That is almost 0.01. Okay? Almost all of it is here. If I added another 0.01, we would have what we started with. Okay? So look at using this equation, folks. I want to know what is the concentration of B if this K sub C is 100. Do is 100. It's the same thing. This whole thing's set up the same. All you gotta do is put 100 there. And you're gonna see that it gets even closer to 0.01. You're making one go away and you're forming the other one. I don't know the answer to this. But if this was 100, then this has to be bigger and this has to be smaller. So anybody want to tell me? I don't know what the answer is. 0.0099. Is that what we say, 99? Okay, so we're almost all over there. And if I said it's 10,000 for K, then I can tell you that rounding everything off with the significant figures you got, B is going to be 0.01. So folks, don't be afraid of this. This is the way you set this up. What you start with, all, nothing. You lose from here, you gain here. If this had broken into two pieces, folks, this would be 2x. Let's stop. Have a good weekend.